Okay, so Graham Lopez, I'm here to talk with you today about programming using OpenACC. So to get started, my name is Graham. That's my email address. Please feel free to email me if you have questions about your code or OpenACC or GPU programming. I don't mind helping out. So don't be shy about emailing me. About this presentation, this isn't really going to be so much about writing code. You can lots and lots of those online with OpenACC. And so really going to try and just get you started up and running with OpenACC, kind of the lowest cost of entry path possible. And then just got a lot of concepts that you're going to run into and that will be necessary for having success using OpenACC. So it's going to be code examples because, like I said, there's a lot of that. Very easy to follow, and more about just a list of things to keep in mind. So related to that, let me acknowledge some sources where I pulled all of this knowledge from. The Keeneland group is the group that I work with. Keeneland is a seed resource. It's a GPU cluster. All of these people are very smart, and they taught me a lot, and I pulled from some tutorials that they had given in the past. Keeneland on supercomputing tutorials and things like that. Also, some people from the OpenACC, or at least that participated in the technical committee discussions, Jeff Larkin with NVIDIA, Michael with BGI, and now James at Cray, they all gave really good talks at various places, and they'll go into a lot of detail about what I talk about in this presentation. Our links to resources at the end, so you can find those for yourself. I highly encourage you to go watch their talks. They know what they're talking about, and they're very informative. And the code samples that I'll show today, you can go and find for yourself. They're actually provided by as part of some of their tutorials. Talk about first, I want to tell you what OpenACC is, what it isn't, and what's important about it. We'll go through some fundamentals just started as quickly as possible. Like I want to give you kind of a very low barrier to entry on this. We'll some code in that section for context. Then optimization techniques. So if you're just a beginner, some of these won't make as much sense to you, but when you're running your own code, you have heard of these things and know where to go and find them. I think that's a huge step up rather than not even knowing that they exist, some of these options. Same thing with advanced features, things that don't really fall under optimization, but things that will help you be more productive with OpenACC. The application for OpenACC came out last year, so I'm going to go over some new features that are in the 2.0 spec. And then I'll do a quick comparison with OpenMP and accelerator capabilities, and then we'll wrap up. Okay. Well, some background. So 4 years ago, a couple of compiler vendors saw that accelerators were being used a lot for general purpose computation. And they started making their own set of directives to try and make programming these accelerators easier. So Core Group had their own set of directives. CAST had their own set, and HTTP compilers. And in the fall of 2010, several members, they formed a working group to try and unify these things to agree on syntax and behavior and standardize the whole thing. So a year later, in the fall of 2011, the OpenACC 1.0 spec was released. And last year, the 2.0 spec has been released. So it's really fast moving and really new. By comparison, OpenMP, has been around for going on 15 years now, 15 years. So, and they're starting to get accelerator support as well. Which is preferable, but I'll give you a little bit of information about that again. Although this is an OpenACC talk, so we're going to focus on it. So there was originally 4 members, TAPS, NVIDIA, and PI. Now, today, there's around 18 members. There's a nice mix of academia and industry, and all as part of this organization. And so, to me, this is encouraging because it says there's a lot of support behind it. There's varied support. It's not just academia. So it's moving forward, but it's keeping the user base in mind. I think it's a nice mix, and they're doing nice things. And so that's really who's behind the specification that gets published. The specification. So then it's up to any implementer that wants to implement it into their compiler. An OpenACC compiler, what exactly are you dealing with? Well, there's 2 main concepts here. It's accelerator and it uses directives. Okay, so I work with GPUs every day, so in the talk, if I start saying GPUs all the time, just substitute that with accelerators. It's really for many kinds of accelerators, and they kind of use a definition for that. So you can get many architectures with OpenACC code. You target multi-core desktop CPUs. You can target core devices like Pi. Some people GPUs, mini-core, that's fine. Different kinds of GPUs, NVIDIA and Radeon both, so DSPs are supported. In the beginning, they were even talking about supporting FPGAs. I think the part that's been dropped, FPGAs are not really covered under OpenACC. All of these other things are. And in fact, people have asked for GPU-specific features in OpenACC that have been rejected just for the sole reason that they are specific use, and they're really trying to support a wide range. Are familiar with programming with directives? They'll look very similar to OpenACC. C, these things are known as pragmas, and really it just comes down to being comments in the code. So if your compiler is not aware of OpenACC or pragmas, it'll just skip them. And if it is aware, then it can use that information. So some of the goals of using directives as opposed to a different kind of programming model, the reason they chose this, really using and directives allows you to hopefully maintain a single source code. So you are maintaining a single source tree, and there's only one path through the code, whether you're using accelerators or not. It's just leads up to the compiler and the runtime, if there is one in the system, but where to place the computation at various spots in the code. But it's still one path through the code. You're not taking different paths based on your good architecture. And from your point of view, you're not taking different paths. High level. So we'll get into this a little bit later, but you're trying to abstract away the details of the architecture by using this. And all people will say that it's a low learning curve. And this is true in some sense, but it's going to it thinking that they're going to do it for you. You might be a little disappointed, and especially when you try to get the absolute performance of your accelerated code. Okay. Countered compiler in a system. What's going to happen? So it does 4 main things for you. It's great parallel code for the target device, so a GPU or something else. It allocates memory on the device. Usually these accelerators have complete separate memories from the system. save memory for you on the device and move there, it's going to execute the parallel code on the device, and then it's going to copy the data back to system memory and deallocate the memory on the device for you. So it does all of these things just from code declarations, these pragmas or directives. All of these steps can be explicitly given or made more specific. The specific you are, the more conservative the compiler has to be about the assumptions. So we'll see a few examples of that later. But just keep that in mind. Using directives is very quick and easy to begin with, but becoming very much detail, at least as much detail as with the full-fledged programming language, the compiler has to be conservative to begin with. So the programming model landscape. So if you want to run code using accelerators, there's kind of a spectrum of how much effort you can put into it. At the low effort kind of thing, you put in libraries, just recalls in your code, or maybe even just relink your code, and that gets executed accelerator. Usually that's pretty low effort. At the spectrum, you have full-fledged programming languages where you're issuing instructions to the accelerator. So examples would be OCL and CUDA. You have to tell it what to do it and how to do it. Directives in between these two things. You're telling the compiler code to accelerate, and you're going to give it some hints on how to do that. But you don't give it all the details. You don't have to know a lot of the architectural details of the target. But it probably is, you have to think about it a little bit more than if you're just going to change out your library call. Direct programming is not auto-parallelization. There are some features of OpenACC that sometimes make it look like it does do a lot of the heavy lifting for you, but it's automatic parallelization, and we'll point that out. So think about it, is you're giving hints to the compiler about what parallelism is in your code and what it looks like. So as a programmer, you still identify the places in your code that you want parallelized, and give more details about how you parallelize it if you want. And you're going to want to do the manage the data movement as well, and we'll see an example of that. The kernel directive, it abstracts even more. Some of this shows large sections of code with the kernel directive, so it starts to look like auto-parallelization, but it's not just going to read all of your code and all of your source files and do everything for you. You like this about what you're going to enclose with the kernel. So I want to try and get you, if you've never seen OpenACC or how to use it, some pointers about best practices maybe. This is going to follow some code from tutorials that exist on the web, like I said, but it's kind of hitting some hints that I wish somebody had told me when I started out using it. So using OpenACC, what do you need? Well, first you need code that you want to accelerate, and it needs to have lots of parallelism. So what do we mean by lots? You'll hear people recommend have at least 10 times the number of threads expressible in your code as you do processors in your target architecture. So for a GPU, you want to be able to express in the thousands of threads in your code. That's parallelism. Most of the time, it's in nested loop structures. And another is these loops be independent, so that loop iterations don't depend on each other. So you large loop iteration because there's with using accelerators, we want to data back and forth between the hosts. So to offset this expense, you need to be able to have enough work that it makes it worth your while. And with the independent loops, we'll do a strict keyword layer can kind of help the compiler identify when this is the case. So right, besides, so you're going to need a compiler that is OpenACC aware. Players are PGI. So they support both India and Radio. GP, they used to talk a lot about also supporting SPI. I'm not sure about the current state of that. I'm curious to know, especially given their recent change corporate affiliation. Is essentially a source-to-source compiler. It's going to take OpenACC and give you OpenCL code in return. Cray actually only, as far as I know, available on Cray systems, but it is also OpenACC aware. They're very active in the specific standard. GCC. So GCC OpenACC support is coming up. There's two active efforts to bring OpenACC into C. It's not ready yet. I'm looking forward to that because that'll give us an open source and free option. The rest of these you have to pay for. You can get trial licenses. And I think probably student discounts as well, but you know, the free option is always nice for learning a new technology. So once you have your compiler, let's just get a feeling really quick for some context of what this looks like. So if you have ACC option, which is, if you don't know what ACC is, it's essentially just a scalar times a vector and add that to another vector. So you can see that really the only thing different in this code is one line in the case of C and two lines in Fortran, and essentially that says you have this concept of structured blocks in Fortran that's not as strict. So you need to tell the compiler when your structured block ends. Really, it's just, and if you open MP before, it looks very, very familiar. It's really just different words in the practice. This is for accelerator. Just really quick what it looks like. And so workflow looks like. Well, it has some bits of code. So this is a 2D, just in 2D simple calculus, essentially what's going on here. And so at the minimum, you're going to take your code, you're going to decorate it with these fragments. Pilot. So the PGI compiler, this ends up throwing at a minimum 2 extra flags, -ADC to turn on OpenACC, and then target or TA for target, and then your target accelerator. You're going to run your code and hopefully verify that you're still getting right answers. So here we can see the loop convergence, and maybe you would print out some notes to make sure that you didn't break anything. And you know, on the accelerator, and it took a little over 2 minutes. So keep in mind the 2 minutes per minute here. Workflow is really about your code. Don't just instance loops and decorate them. I mean, that's an okay place to start, but you'll hire returns if you really think about the parallelism in your code and how it's expressed. Maybe already some support in there in the form of OpenMP. So you can use that as a hint. Maybe you want to replace those with OpenACC calls, or maybe you want them to work together. after you ponder what you want to do, you can decorate it before, you compile, and there's actually some analysis you can do at compile time. So if you give the CGI compiler, and most of the other compilers have something where give it dash in info equals Excel flag. It'll do it in relation to generating accelerated code. So it's going to tell you at line 55 in the code, I'm going to do data management, and it says, okay, I'm going to generate this is data code because that's what you asked for. There's several compute capabilities I'm baking into the binary. You can find this, you can specify, no, I want 3.5 or I just want 2.0. Line 6, it says, okay, I recognize that this loop is parallelizable, so I'm going to do that. So it says accelerator kernel generated. It gives you some details about how it's mapping to the hardware. If you're a CUDA programmer, these block IDX things will look familiar to you. If you don't worry about it. The whole point of OpenACC is to abstract those things away. And it actually does this in 2 different places because we decorated 2 spots. And so at compile time, it's good to read through this and make sure that what you expected the compiler to do based on your it's at. If there's some hidden loop dependencies, or if the compiler can't figure out that the loops are independent, it'll say, it'll tell you that the loop is parallelizable. It'll say that it's not. And so you check for that. Because if it's not parallelizable, it's not going to generate kernels, and it won't be running on the accelerator, and you'll wonder why your code is going. Some compile time analysis and checking. You run your code, and you can actually get some output, some of this stage as well. And by at time asking for it, or you can, most compilers support an environment variable. So for instance, with PGI underscore AD underscore time equals 1. And if you run your binary, it'll give you some detailed timing information. So the time at the top, that's from the own instrumentation. But even without any instrumentation at all, you timings about what's happening with the device code. So at line 55, the data copy in, code was reached 1,000 times. We launched 1,000 times. That's what's actually doing the computation. So it gives some information about the geometry of how it's mapping that parallelism to this with the grid and blocks there. You get information about copy out and the other data movements and kernels as well. So you can check this and make sure that what you expect to have happened is happening. The kernel is being launched and run on moving forward. We'll talk about some optimization. So that's hopefully a better, a more comprehensive workflow. So if you're in the OpenACC tutorials before, you've seen this example and you know the punchline, but essentially it asks for parallelization. Most likely your code is going to go slower than if you didn't have any accelerator at all. Even for one OpenACC thread, the accelerator version is going to be slower in a lot of cases. And why is this? Well, besides identifying the parallelization in your code is to identify how data should be managed. Like I said earlier, the compiler should be very, very conservative about and so OpenACC gives you the ability to tell the compiler, this is exactly how I want the data moved and when to move it, importantly. So you have this data, this ACC data directive, and there's different clauses you can give to it. So copy will allocate the device memory for you and transfer on and exit to that code block where the data is the same, except it's only going to transfer on entry, etc. Create only allocate the memory for me. The data moved somehow at a different spot. Because the data is already there, so don't allocate anything for me. Don't move it. Present is important because parallelization, a compute region. So as to a data region, the compute region where you say ACC parallel loop. If every variable it sees in that region, it's going to try and get to the device somehow or another. You put your variables in the present list to say you're going to encounter this in the compute region within the data region that I'm telling you about, but these variables are already there, so don't worry about them. Present or, so star is really anything else above in this list, and that says, that kind of combines present and the others. Essentially check to see if it's there, and if it's not, then do the thing I'm asking. You have to tell the compiler when to move data. So that if you don't, what's happened is moved in and out off of the device across the PCI bus at every loop iteration. So for all 1,000 loop iterations, moving data in and moving it out. But usually what happens, as in this example, is you really don't care about the data at the beginning, before the loop ever starts. You care about the starting value, and then you care about the ending value. You don't care about the value between loop iterations. And so you have ACC data well outside the computation region. And that says only copy A in at the beginning of this while loop and copy it out at the very end. They'll do it for every iteration of the nested for loop. And new is just a temporary value that lives on the device. So allocate that for me on the device, but don't worry about moving it in or out. It's just new. If we do this, what we'll find from a little over 2 minutes to about 8 seconds. And you can see down here at line 50, it says data copy in reached 1 time, where we saw that it was doing that 1,000 times. The saving is essentially that you're realizing is 1,000-fold worth of data movement across the PCI, which comparison is very slow. So here's our updated table, and we get about 14x over the one thread version, without a 7 or 6x speed up over the 8 core version. So not too bad. You see how this is kind of getting a little further from auto parallelization. You're having to think of what's going on in your code, and compiler can't do everything for you. It'll do enough for you to get the code running on the device, and usually if you don't do anything crazy, you'll get correct results. Like I said, conservative about the assumption. Compiler ministers are only error on the side of giving you correct results rather than fast executing code. That's true whether you're talking about accelerate or not. Give you correct. At the end of fast doesn't matter if it's wrong. The first thing you'll encounter very early on, once you figure out this data movement thing and work through a few examples of that, is there to be 2 directives for creating compute regions that you think. You have this ACC parallel loop, and you have ACC kernel. And which do I choose, and which is? So there's a real that was published, I don't know, probably a year and a half ago, and PGI website. I have a link to that at the end presentation. It goes into a lot of detail about this, but the way to think of it for right now is kernels is your allocator to do more analysis for you. So you can enclose a large code region with the kernel directives. You're a compiler to generate as many devices as you want. And whatever it thinks is appropriate. So the compiler to do a lot of analysis for you. Parallel, on the other hand, is telling the compiler, I definitely want this specific loop turned into a kernel. So it parallel create code whether or not the loop is independent, whether or not you're going to get correct results. If you parallelize that loop, it'll do it because you have to do kernels. You're letting the compiler decide whether or not to do it. Key similarities that going the parallel route is more similar to using OpenACC. So if you're an NP programmer, you might gravitate to that to begin with. Most I see parallel, and I think that's probably for a couple of reasons. One, because you have to decorate the loops that you want, and there's more of a direct correlation between the directed place and device or kernel that you're getting. It's more clear looking at the code, what's going on, what exactly is being moved to the device as far as computation is concerned. And because it's easier, you're giving the compiler less freedom. Sometimes it's easier to optimize using parallel, I think. Opinion, I suppose. But eventually, you'll probably find yourself using parallel. But kernel, the time, they're both telling the compiler to generate device code that after you've told the compiler that you have very little control over it. So they're both, and they can perform equal. So it's not that kernel is slower, but you have less control. And programmers, a lot of programmers don't like that. Some other miscellaneous things to start out with your data. You may not want to move all of the memory associated with a variable. And so we have this ability for array shaping. If you're a Fortran programmer, this probably isn't as necessary. Fortran arrays, they around with them as far as the compiler is concerned, information about how memory is associated with that array. In C, we the same here. And so that means in this case is essentially that it's harder for the compiler to figure out how much is associated with this pointer. Even before, you'll find yourself using this probably more often in C, but it's useful for both because it can also save you on unnecessary transfers, right? Maybe you only want the accelerator to work on a small piece of a large array, and so you can open to only move part of it instead of the whole thing, and so yourself on some data transfer cost. Sort of starting to get into a kind of option. It's just easier to write the surrounding logic if you've got an entire array instead of having to ensure working on the piece you want. If you only transfer the piece you want, now you can work on the whole thing. So present, we saw, and it says this is already there. So nice thing this allows is that you can move your data regions higher in scope. They don't have to be as tightly coupled to your compute region. And because it allows you to start moving data to the device as soon as it's ready to go, even if there are things that have to happen before you want the device code to execute and do the computation. Moving regions up allows you to get a long lifetime for that data on the device, so you're maybe avoiding unnecessary transfers. And it can see if that data has had a chance to transfer before your code gets to the part where it's going to launch the device computation kernel. If the data's been transferred long ago, that kernel can start immediately rather than having to wait for the transfer to finish. So in general, you want to move your data regions as high up your application scope as is reasonable. A little bit. So we'll look at some advanced optimization. You get ready to optimize. Well, first thing you want to do is profile. And there are ways to do this. We saw the compile time sort of filing. We have info Excel. You can get put at runtime from most compilers, like I said, with CGI ACC time equals 1. Depending on your target architecture, maybe you have other vendors or third-party tools for NVP. NVProf, NVVP, they work fine with OpenACC code. You'll get all of that information that you're used to seeing about kernel execution on the device. There are tools like TAO and TotalView. These, again, it depends on the vendor support, but for example, NVIDIA has the kubectl library, which it is hardware counters library form, so tools like TAO can read the counters and give you detailed traces and profiles. To optimize, the first thing you might want to do is fine-tune how the parallelism goes to the so the examples of parallel vectors are that execute in lockstep. If you're a Java programmer, you might think of these as threads, as CUDA threads. This is your SIMD, SIMT level of parallelization, the vector. A worker is specified to contain one or more vectors. And pretty much specified to contain one or more workers. There's a game. Have one or more shared resources. They're allowed to share resources, I guess I should say. So these might be device cache or shared memory, streaming multiprocessors. Multiple games can work independently, so they're not working in lockstep. If you're a CUDA memory, these things might correspond to game, might correspond to blocks and workers for work and vectors, threads. But OpenACC is just a specification, and it leaves computation up to the compile, the compiler. So they can expose these levels of parallelism in different ways within that specification. So you can do like this, but it could be dangerous. In general, probably not. Some notes. For instance, on NVIDIA GPUs, vectors should be multiples of 32 because that's your work size. And to start out with, just ignore the worker construct. 9% of the time, you don't want multiple workers, and instead you just want really long vector links that are multiples of 32. So like vectors of 256 or 512, you'll get your best performance that way. Some more optimization. OpenACC allows for asynchronous execution. This is really useful for overlapping multiple kernels running at the same time, memory transfer overlapping with kernels. Every directive in the spec can have an async clause on it, where you get an integer handle, and essentially what you're doing is creating queues denoted by these integer handles. If you access data in a certain queue with your data regions and your data directives, you have to wait before you're allowed to do that. Asynchronously wait. You think about that and get that in your mind. What that really is meaning is that you're combining more queues together. What I have encountered in the past in older compiler versions that you may not get bidirectional PCI bus. I mean, when I say memory transfer, you may not get bidirectional overlapping, even asynchronously, because for NVIDIA GPU, you have to use pinned memory to transfer that, and OpenACC doesn't ask for pinned memory. So new versions may have fixed that, and I think Cray does that for you by default. But just out for that. If your memory transfers are overlapping, check out and make sure you're getting non-page lockable memory. So asynchronous execution can also be beneficial if you don't have the possibility of overlapping your transfers and computation. And for this is you can reduce your CPU latency. Essentially, you can asynchronously submit work to the device so that even if it's dependent on each other, it's there to go. Kernel gets encountered. And useful, Cray even gives you a flag to do this for you. So consider that even if you don't have opportunity for overlap. Keywords, so you have to update your code to C99 to use this. And essentially what restrict does is it your main promise to the compiler that this memory is not referred to by any other name except the form declaring with the specifier. And so this can help the compiler be sure that certain regions of memory are dependent on any other loop iterations or any other kernel running, because it can keep track of which you've given that memory and where exactly that pointer is being manipulated. We have a Wikipedia article for this, the restrict keyword, and it explains it really well. That's recommended. Loop tree. This has to do mostly coalescing. If you're a programmer, you will learn about that concept. But just you want your inner loops to be strong, meaning they access adjacent memory locations. You large amounts of contiguous memory for your outer strides, your outer loops. So you accelerators have a very high bandwidth memory, and that means that they're fetching large words of memory at once. So instead of fetching, 16 or 32 bits at a time, they're fetching maybe 300 or 512 bits at a time. So your loop geometries can play a role in the performance of your code if you know the architecture. Is a new directive in OpenACC 2.0. I've heard mixed about how good it is, but it tries to do some of it for you. What else? So we talked about that loop vision and fusion. So maybe you want to combine smaller loops together or set large loops apart. So these seem to be competing ideas, and they are. So it's really a trade-off between launch latency. So whenever you launch new kernel for small loops, you need to make sure that there's enough work in the loop to justify the cost of launch that on the device. If the loop's too big, you have finite resources on the device, such as the registers each thread can use and the amount of shared memory there is, cache, things like that. When you start with resources, you're going to get a lower occupancy on the device. You're not going to populate as many threads as you would otherwise. And so you have too much computation happening in your loop. So you need to find a nice balance. There's a collapse that the loop fusion for you. So that's nice. You can do target specific tuning. With this clause, kind of conditional says if I'm on device type and video, do this stuff. This API calls to do the same thing. You can use the if-defs. If-defs are not optimal because some compilers let you pack multiple code will target devices into a single binary. And so if-defs, you're essentially giving up that functionality. Some features really quick. Interoperability. OpenACC, they've really tried to design it to be interoperable with other programming paradigms, so you can use it within CUDA code or OpenCL, OpenACC. So that's a GPU-specific feature. So the 2.0 spec only suggests functions interacting with streams, but doesn't require that from implementers. Use a thrust library in C++. You can pass your thrust vectors to device pointers, so that's nice. Host data allows you to use device memory, but some libraries require that you pass it up to host pointer, and so data lets you get around that. Device pointer is the thing. If you already have device memory allocated, this says that the pointer is already a device type pointer, so that's useful for if you're using CC within code that already has, say, CUDA in it with CUDA map. AC map data is kind of a more general version of that. It says associate this pointer with this device memory. And it's powerful. Jeff Larkin gave the example of you can use AC map data to create sliding windows. So if you have memory that's too large to fit on the GPU, you can do a sliding window by remapping your pointer as you go to work on larger pieces of memory than you would otherwise. You will train all in one shot. What's next? So data directive update. There's a large cost with setting up and tearing down multiple data regions. So you want to have data regions that you want, and I told you earlier you want them in high scope. So this means there's going to be potentially a lot of code, both code and device code, happening within a data region. So maybe one particular variable you want to check an intermediate value, or you want to bring back to the CPU to combine with some other value, send back to the device. Up you do that, you can kind of cherry pick in a very specific spot. Point update host has become update self. That's if you update host, it's essentially to accommodate nested parallelism. So it's more general. So update host has been updated. Data regions, I'll do that in a second. So the API call to almost everything you can do with a data directive, you can do with a API call. And so it's useful for, mostly for C and C++, deep copy, for doing manual deep copies, which is if you have a complex data structure that has pointers, indices, which themselves are arrays of pointers pointing to other, being able to tell OpenACC with directives how to copy that only a single piece of that can be difficult. So with these things, you can pass it an exact memory address, for example. malloc and free, this is kind of a portable way to get device memory. And if you don't want to explicitly call CUDA malloc or free, you can use these, and it will work on Radeon GPUs or on multi-core, or whatever you want. So, new fees in OpenACC 2.0. Bean directive. So before you had a function called from within a compute region. If the compute didn't inline it would choke. So it had to inline everything. This lets decorate your function call and tell it how to do the parallelism, to generate code for things like that. And if a call like a function call that's maybe 3 calls, you have to decorate the entire stack. You can't just decorate one that's actually going to execute it. There's multiple device types. So with this device type NVIDIA, say you can specify different vectors whether you're on NVIDIA or Radeon. So that helps with the optimization efforts for multiple platforms. Really what this is your data doesn't have to be a C block anymore. They be in different scopes. Your enter data and your exit data can happen in different scopes. And the most obvious example of this is C classes. After you enter your data region, your disruptor, you exit your data region. Region as many times as you want, you only exit it. Gotcha. That. In OpenACC 2.0, so only one thread, read at a time, write at a time. Update capture is just update plus store the result for later. And other things I haven't mentioned, parallelism, essentially dynamic parallelism. And procedure calls, no more. Already talked about that. Data management, you can have device resident global data, global variables now. Async behavior, so there's been additions to the async clauses, really for control flow. New API routines for C, C++, atomic. Default none is nice for debugging. If you don't want ILR to do any data management for you, make no assumptions. So, and it lists in the front of the document all the new things since the 1.0, if you're familiar with 1.0. Just really quick, there's some details here that I'm going to gloss over. There's no production ready. So to get accelerator support in OpenACC, it's only up in the 4.0 spec, and there's no production ready 4.0 compiler for CPUs. There's compilers. OpenACC was designed from the start to be interoperable with OpenACC, so you can mix and match as much as you want. And here's a comparison of what they look like. Simply, you pragma directives in both cases, just the words change, and they mean somewhat different to the compiler. So a few major differences are how the parallelism happens in OpenACC. Telling the compiler to offload this section of code and actually do the execution, those things happen at once. In OpenACC, you do those in separate steps. So OpenACC exposes more to the programmer. You can do copies and things like that, whether or not the data is there or it's not. In OpenACC, it's always going to do I have to see if it's already there. Differences in the way you do comes from within regions. Regions. So I guess you have multiple entries and a single entry. You have the same number of enters and exits. There's an exit. I don't think they finished the spec for that for 4.0, but they're working on it and it should be coming very soon. The aspect of the region now. Okay, I went really fast through that. You can ask me questions about it. I think I'm running time here. What's in the next OpenACC version? OpenACC is really in the technical committee, and they're pretty big to do. They prioritize their to-do list, the specification based on user feedback. So the routine directive and everybody wanted that. They didn't want to have to rely on their function. So that's been asked for that are coming are a better way to do deep copies, helps out with complex data sets that you find in these large scientific codes, interfaces. So a more straight to do profile support and things, and debugging especially, enhanced support for those things. OpenACC fairly quickly and it's driven by user demand, so that's one nice thing about it. And the thing I kind of like about it over the OpenACC, a much bigger committee, their accelerator committee, it's a subcommittee, and so it's even bigger than the OpenACC committee. And so anyway, it moves slower. It's a much more mature standard, and they're very careful. They kind of watch to see what mistakes OpenACC makes, and they try not to make mistakes. OpenACC, they just try and fix them or next step. Here are the promised resources, lots and lots of tutorials. Like I said, I mentioned at the beginning, Jeff James Baker. All of them gave talks this year at ETC, and those videos are available on ETC site. Tutorials from my group, and the OpenACC website has links to lots of resources. So that, you take questions if you have any.